Hello everyone, I'm Madam Sheila and today we'll be learning Chapter 4, Threads and Concurrency. So this chapter consists of an overview of what threads and concurrency are in multi-core programming, multi-threading models, thread libraries, implicit threading, and threading issues, and lastly, operating system examples. These are the objectives that we're trying to achieve today. It's to identify the basic components of a thread and contrast threads and processes, to describe the benefits and challenges of designing multi-threaded applications, to illustrate different approaches to implicit threading, including thread pools, fork join, and grand central dispatch, and to describe how the Windows and Linux operating systems represent threads, and designing multi-threaded applications using the pthreads, Java, and Windows threading APIs. Motivation. Most modern applications are multi-threaded. Threads run within application. Multiple tasks with the application can be implemented by separate threads. Update display, fetch data, spell checking, answer network requests. Process creation is heavyweight while thread creation is lightweight. Can simplify code, increase efficiency. Kernels are generally multi-threaded. This is a single and multi-threaded processes. One example we can see here is a web server. Multiple threads allow for multiple requests to be satisfied simultaneously, without having to service requests sequentially or to fork off separate processes for every incoming request. The latter is how this sort of thing was done before the concept of threads was developed. A daemon would listen at a port, fork off a child for every incoming request to be processed, and then go back to listening to the port. There are four major categories of benefits to multi-threading. The first one is responsiveness. It may allow continued execution if part of process is blocked, especially important to user interfaces. The second one is resource sharing. Threads share resources of process easier than shared memory or message passing. The third one is economy. It is cheaper than process creation, and thread switching lower overhead than context switching. Scalability. Process can take advantage of multi-core architectures. Multi-core programming. Multi-core or multiprocessor systems put pressure on programmers, and the challenges include dividing activities, balance, data splitting, data dependency, testing, and debugging. Parallelism implies a system can perform more than one task simultaneously. Concurrency supports more than one task making progress. Single processor or core scheduler providing concurrency. Concurrency versus parallelism. Concurrent execution on single core system looks like this, and parallelism on a multi-core system looks like this. There are two types of parallelism. The first one is data parallelism. It distributes subsets of the same data across multiple cores, same operation on each. And the second one is task parallelism, distributing threads across cores, each thread performing unique operation. This is data and task parallelism. Amdahl's law identifies performance gains from adding additional cores to an application that has both serial and parallel components, as a serial portion and processing cores. That is, if application is 75% parallel or 25% serial, moving from 1 to 2 cores results in speedup of 1.6 times. As n approaches infinity, speedup approaches 1 as Serial portion of an application has disproportionate effect on performance gained by adding additional cores. But does the law take into account contemporary multi-core systems? This is the Amdahl's law. User threads and kernel threads. User threads. The management is done by user-level threads library. And there are three primary thread libraries: POSIX pthreads, Windows threads, and Java threads. Kernel threads is supported by the kernel. For example, virtually all general-purpose operating systems, including Windows, Linux, Mac OS X, iOS, and Android. This is user and kernel threads. There are three multi-threading models, which is many-to-one, one-to-one, and many-to-many. In the many-to-one model, many user-level threads are all mapped onto a single kernel thread. Thread management is handled by the thread library in user space, which is very efficient. However, if a blocking system call is made, then the entire process blocks, even if the other user threads would otherwise be able to continue. Because a single kernel thread can operate only on a single CPU, the many-to-one model does not allow individual processes to be split across multiple CPUs. Green threads for Solaris and GNU portable threads implement the many-to-one model in the past, but few systems continue to do so today. The one-to-one model creates a separate kernel thread to handle each user thread. One-to-one model overcomes the problems listed above involving blocking system calls and the splitting of processes across multiple CPUs. However, the overhead of managing the one-to-one model is more significant, involving more overhead and slowing down the system. Most implementations of this model place a limit on how many threads can be created. Linux and Windows from 95 to XP implement the one-to-one model for threads. The many-to-many model multiplexes any number of user threads onto an equal or smaller number of kernel threads, combining the best features of the one-to-one and many-to-one models. Users have no restrictions on the number of threads created. Blocking kernel system calls do not block the entire process, and processes can be split across multiple processors. Individual processes may be allocated variable numbers of kernel threads depending on the number of CPUs present and other factors. Windows with a thread fiber package, and otherwise it's not very common. One popular variation of the many-to-many model is the two-tier model, which allows either many-to-many or one-to-one operation. It is similar to many-to-many except that it allows a user thread to be bound to kernel thread. IRIX, HP UX, and True64 UX use the two-tier model, as did Solaris prior to Solaris 9. Thread library provides programmer with API for creating and managing threads. There are two primary ways of implementing it. The first one is library is entirely in user space, and kernel level library is supported by the operating system. POSIX threads may be provided either as user level or kernel level. A POSIX standard for thread creation and synchronization. Specification, not implementation. API specifies behavior of the thread library. Implementation is up to development of the library. And it's common in Unix operating systems like Linux and Mac OS X. Okay, here is an example of POSIX threads. You can pause the video if you want to take a longer look at it. This is Windows multi-threaded C program. Java threads are managed by the Java virtual machine. It is typically implemented using the threads model provided by underlying operating system. Java threads may be created by extending thread class and implementing the runnable interface, and standard practice is to implement runnable interface. Okay, so here is how we can implement runnable interface. Create a thread and wait on a thread. Rather than explicitly creating threads, Java also allows thread creation around the executor interface. And the executor is used as follows. Here's a continuation from the previous slide. And this one too. Implicit threading. Growing in popularity as numbers of threads increase, program correctness is more difficult with explicit threads. Creation and management of threads are done by compilers and runtime libraries rather than programmers. There are 5 methods that can be explored, which is thread pools, fork join, OpenMP, Grand Central Dispatch, and Intel threading building blocks. So thread pools. Create a number of threads in a pool where they await work. The advantages are usually it is slightly faster to service a request with an existing thread than create a new thread. It allows the number of threads in the applications to be bound to the size of the pool, and separating tasks to be performed for mechanics of creating tasks allows different strategies for running tasks. Like, for example, tasks could be scheduled to run periodically. And Windows API supports thread pools. As you can see down below, these are the 3 factory methods for creating thread pools in executors class. Fork join parallelism. Multiple threads, which are tasks, are forked and then joined. This is a general algorithm for fork join strategy. Fork join parallelism in Java. The fork join task is an abstract base class. Recursive task and recursive action classes extend fork join task. Recursive task returns a result via the return value from the compute method. Recursive action does not return a result. Open multiprocessing is a set of compiler directives and an application programming interface for C, C++, and Fortran. It provides support for parallel programming in shared memory environments, and it identifies parallel regions, which blocks of code that can run in parallel. Grand Central Dispatch. Apple technology for Mac OS and iOS operating systems. Extensions to C, C++, and Objective-C languages. API and runtime library. It allows identification of parallel sections, and it manages most of the details of threading. Blocks are placed in dispatch queue. It is assigned to the available thread in thread pool when removed from queue. There are 2 types of dispatch queues, which are serial and concurrent. For serial, blocks are removed in FIFO order and queue is per process, which is called main queue. Programmers can create additional serial queues within program. And the next one we have concurrent, removed in FIFO order, but several may be removed at a time. In the fourth system-wide queues are divided by quality of service, as you can see down here. For the Swift language, a task is defined as a closure, similar to a block minus the caret. Closures are submitted to the queue using the dispatch async function. Intel threading building blocks. It is a template library for designing parallel C++ programs. And here is a serial version of a simple for loop. The sim for loop is written using TBB with parallel for statement. Threading issues, semantics of fork and exact system calls, signal handling, synchronous and asynchronous, thread cancellation of target thread, asynchronous or deferred, thread local storage, and scheduler activations. Semantics of fork and exact. Does fork duplicate only the calling thread or all threads? Well, some Unixes have two versions of fork. Exact usually works as normal. Replace the running process including all threads. Signals are used in Unix systems to notify a process that a particular event has occurred. A signal handler is used to process signals. Signal is generated by particular event. Signal is delivered to a process. Signal is handled by one of two signal handlers, which are default and user-defined. Every signal has default handler that kernel runs when handling signal. User-defined signal handler can override default, and for single-threaded, signal is delivered to process. Where should a signal be delivered for multi-threaded? Deliver the signal to the thread to which the signal applies. Deliver the signal to every thread in the process. Deliver the signal to certain threads in the process, and assign a specific thread to receive all signals for the process. Thread cancellation. Terminating a thread before it has finished. Thread to be cancelled is target thread, and there are two general approaches to it. The first one is asynchronous cancellation terminates the target thread immediately, and the second one is deferred cancellation allows the target thread to periodically check if it should be cancelled. POSIX thread code to create and cancel a thread looks like this. Invoking thread cancellation requests cancellation, but actual cancellation depends on thread state. If thread has cancellation disabled, cancellation remains pending until thread enables it. Default type is deferred. Cancellation only occurs when thread reaches cancellation point. For example, POSIX thread task cancel. Then cleanup handler is invoked. On Linux systems, thread cancellation is handled through signals. Deferred cancellation uses the interrupt method, which sets the interrupted status of a thread. A thread can then check to see if it has been interrupted. Thread local storage allows each thread to have its own copy of data. It's useful when you do not have control over the thread creation process, like when using a thread pool. It is different from local variables. Local variables are visible only during single function invocation, and thread local storage is visible across function invocations. It is similar to static data. Thread local storage is unique to each thread. Scheduler activations. Both many-to-many and two-level models require communication to maintain the appropriate number of kernel threads allocated to the application. It typically uses an intermediate data structure between user and kernel threads, lightweight process. It appears to be a virtual processor on which process can schedule user thread to run. Each lightweight process is attached to kernel thread, and how many lightweight processes are there to create? Scheduler activations provide upcalls, a communication mechanism from the kernel to the upcall handler in the thread library. This communication allows an application to maintain the correct number kernel threads. Operating system examples: Windows threads and Linux threads. Windows threads. Windows API or Windows Application Programming Interface is primary API for Windows applications. It implements the one-to-one mapping at kernel level. Each thread contains a thread ID, register set representing state of processor, separate user and kernel stacks for when thread runs in user mode or kernel mode. Private data storage area used by runtime libraries and dynamic link libraries. The register set stacks and private storage area are known as the context of the thread. The primary data structures of a thread include ETHREAD, executive thread block, which includes pointer to process to which thread it belongs and to kthread in kernel space. Kthread, kernel thread block, scheduling and synchronization info, kernel mode stack, pointer to TEB in kernel space. TEB is thread environment block. Thread ID, user mode stack, thread local storage in user space. This is Windows threads data structures. To the last slide of this chapter, and it's about Linux threads. Linux refers to them as tasks rather than threads. Thread creation is done through clone system call, and clone allows a child task to share the address space of the parent task process. Flags control behavior. The flag clone fs means file system information is shared. Clone VM means the same memory space is shared. Clone sighan means signal handlers are shared, and clone files means the set of open files is shared. Struct task struct points to process data structures, shared or unique. That's all for chapter 4. I'll see you in the next chapter. Bye!